Alright, it's time to talk about colligative properties of solutions, and that's a really big word, but pretty much what it means is just that it's properties of solutions that are different from the ingredients themselves. And that's the first thing that I have up here, is that when you have a solution, it's not going to act exactly the same as it did before it was a solution. For example, water has a boiling point of 100 degrees Celsius as a normal boiling point, but when you make it a solution and you dissolve something in the water, its boiling point is not going to be 100 degrees anymore. It's either going to go up or down depending upon what goes into it. So you have the definition right here of a colligative property. And there are three types of colligative properties listed for you below: vapor pressure lowering, boiling point elevation, and freezing point depression. And we're going to look at each one of those individually. The first thing that we have is vapor pressure lowering. And it's simply the idea that when you have a solution, the vapor pressure of the solution is lower than it was as just a pure solvent. And, I explain why on here. And it says that solutions have water molecules that surround the solute, which makes it harder for them to leave and become a gas at the surface of the liquid. It's like they're being weighed down by the solute particles. And so that lowers the vapor pressure. It says that the vapor pressure is proportional to the number of particles of the solute. What that means is if you have twice the number of solute particles, then you have twice the decrease in vapor pressure. If you have 3 times the number of particles, then you have 3 times the decrease in vapor pressure. The identity of the solute can vary how much the vapor pressure is lowered. So in other words, if you can remember, we watched Tyler DeWitt's video the other day about dissolving. So like if you have an ionic compound, remember it breaks apart completely into ions, whereas the covalent compounds stay together in groups. They break apart, but they stay together in molecules. That means the ionic compound broke apart into more pieces, and therefore it can have a greater effect because you have more little chunks hanging out in the water to hold it down than with a covalent compound. With freezing point, we're basically going to be describing the same thing. The freezing point gets lower in solutions. It drops down. So when you put something into water, you actually make it more difficult to freeze it. So for example, when they salt the roads in the wintertime, they put salt on the road because the salt lowers the freezing point. Remember, freezing point is the same thing as the melting point, so that also lowers the melting point. That means that it has to be colder in order to freeze the water. I address why again. It's kind of the same idea. The solute particles, when they're in solution, basically what they do is they keep the solvent from coming together in an orderly arrangement like it normally would in order to form a solid. So like if it's water makes that honeycomb structure. The salt gets in the way and won't let it form that nice little honeycomb structure quite as easily, and it just makes it harder to freeze. And it does say again, the amount of freezing point depression is proportional to the number of solute particles. So again, if you double the number of solute particles, you double the effect on the freezing point. The last is boiling point elevation. So what this means is that when you have a solution, the boiling point goes up. So if you put salt in water, it's going to boil at a higher temperature than 100 degrees Celsius. And if you remember back to our discussion of vapor pressure in a previous unit, vapor pressure, like the boiling point is where the vapor pressure equals the outside pressure. So we've already said that solutions have lower vapor pressure. That means that it's going to be harder to get enough gas at the surface of the liquid to reach the boiling point. So it makes it harder to reach the boiling point. You have to add more energy in order to make it happen. And the why is right here. If the vapor pressure is lowered by the solute, then it's just simply harder. It's related entirely to the vapor pressure lowering. It says that the amount of the boiling point elevation is proportional to the number of solute particles. So that means, again, like if you double the number of solute particles, then you should double the effect on the boiling point elevation. In other classes, at times we may go on to calculating colligative property with vapor pressure lowering and boiling point elevation. If you want to try to grab yourself some extra credit for this upcoming test, we're in a little bit of a hurry mode, you can go to the YouTube playlist that I have linked for Chapter 16, and you can check out the videos on calculating freezing point depression and boiling point elevation, because there will be at least one of those on the test that's coming up. It's going to be entirely optional, but hey, it's a way that you could get a little extra credit if you want to try for it. So feel free to check this out on the playlist that I link on Google Classroom, and we'll talk about the rest of this in class.